So I'm from University Center in Svalbard. So in second slide, replying question where it is. It is 70 degrees to the north, halfway between Norway and North Pole. It is very much on the north, but it is not very cold because of Gulf Stream action. So then what we are doing there? There is University Center in Svalbard belonging to Norwegian Ministry of Science and Education, and according to the rule, we have 50% students from Norway and other students from all world. And in Department of Arctic Technology, we provide teaching of future Arctic experts about ice mechanics, ice physics, and loads on structures. And within course program, each year since 2007, and where is point? I'm going with students in the Barents Sea by ship. So it is usually in April, May, and we need to pass marginalized zone and to find proper flow, so then students can go on the floor and work to study physical and mechanical properties of ice. It is important that students are on the place in the first time. So, reason to study wave for me. So my talk actually about, it is my opinion about what is going on in this region. And gravity waves can first of all destroy ice relatively quick and over big areas. So then after that even it is impossible to find proper flow to work on the ice. So, and after that ice became different. It drift faster, it heat fluxes are different, so and of course it influences different types of loads on structures if they are planned for the design in this region. So then I want to show this video. We already saw many such type of videos during this session. There is wave, it is marginalized zone. So then wave amplitude, I would tell here about 1 meter with wavelength about 100 meters. So there are 3 accelerometers deployed on flows, and the length of a wave is much bigger than the size of flows. And if you will see, actually collisions between floors are almost not happen. Everything is very smooth. And another thing is that there are not so many vertical relative displacement between flows. So then I want to go back to presentation. And so then main assumptions which I will use for my talk. Flow diameters much smaller wavelengths. Flow collisions are rare even for not confined ice. I can show similar movies where with flow collisions, but it is near shoreline, not in the open sea. Relative displacement flows and vertical displacement are small. Horizontal velocity of flows relatively water particles can be significant. Wave damping occurs over distance which much larger the wavelength, so therefore we may use standard dispersion equation describing wave propagating in the marginal ice zone, which slightly modified. So then our situation is here. So again, wave typical wave period 10 seconds, wavelength 100 meters, wave amplitude about 1 meter. So then amplitude of water velocity in such wave could be about 1 meter per second, and it also, this type of difference can be between flow velocities and water velocities. So if we consider viscosity in upper layer, and here I refer to papers of De Carollis, who estimated slush velocity less than 10 in third power, even in such high, with such high kinematic velocity of top layer, we may consider boundary layer below the ice, which thickness delta is estimated with such formula using standard solution about oscillating boundary layer, and this thickness is much less than flow diameter. So still we can consider it like boundary layer near floating oscillating plate. Momentum balance of floating ice just in projection on deformed ocean surface consists of inertial term, projection of gravity force, viscous force applied from the water, and force responsible for flow-flow collision. And further I will consider periodical motions. So in that case, inside the boundary layer, I can write that velocity consists of two parts. And one part is velocity induced by wave. It is similar as in the wave with the same frequency and amplitude, but without ice. And the second addition is due to the no-slip boundary condition between ice and water. So then in this situation, we have this equation describing boundary layer velocity with boundary conditions, specifying at the boundaries of the layer. And the solution is very simple. So then here we have boundary layer thickness. It was introduced before. So this solution is just extension of classical Stokes problem about oscillating plate. In our case, if we would have fixed flexible plate, not drifting, not moving, so then we have out below the plate oscillating velocity field due to the penetrating wave, and below the plate we have a boundary layer. So the energy damping is calculated with a standard formula like integral over the thickness of boundary layer from second power of velocity gradients, and it is expressed with this formula and depends on viscosity and frequency. So then further I will deal with effective viscosity, or I will call it eddy viscosity. So then if we use these formulas in equation for moment balance of flows, so then I may derive that ice velocity is proportional to water velocity with some coefficient. So this coefficient is very simple. Actually, this formula, let me check, follows from this assumption that the force of flow-flow interaction in linear approximation is proportional with some coefficient kappa to the amplitude of flow motions. Then we have this coefficient in this formula, and here we have viscosity. So, but further I will not look deeper into this formula, and I will try to extract from experiment the value for this coefficient and the value for the viscosity in the boundary layer below the ice. So then the damping of wave energy is calculated with this formula. If I average it over the wave period, I will have another formula. So then if we assume that coefficient alpha is equal to 0, what means that ice moves just the same as water, no difference. So then dissipation is 0. So then if I have small floating body, and this body is in equilibrium with water, we just can replace this body and place instead this body water. and then dissipation is 0. So if alpha equal to 1, so then the film is flexible but not moving. Then we have another approximation for energy damping, and it is just the same as was introduced by Jan-Erik Weber 1987 in paper where he considered two viscous layer model. So special attenuation wave can be expressed through this formula because we need to take into account group velocity here. So then all these coefficients, they depend on water depth, wave number, wave frequency, because wave amplitude is related to water velocity induced by wave through coefficient depending on these variables. So again, I go back to these accelerometers deployed 5th of May 2016 drift ice in the Barents Sea. So then each of accelerometers measure acceleration and angular velocities and acceleration along self-axis, angular velocity along axis, and angles between magnetic vector and self-axis. So then here I have set of formulas, but it is interesting that if I will the xs, for example, that is real quantity which is delivered by accelerometer, and this is the sum of acceleration, real physical acceleration, plus g theta, where theta is angle, and angle is small, so therefore theta is proportional to derivative. So then if I take it into account, so then if we consider acceleration of water particles without in the water with open surface without ice, so then this term is just proportional to acceleration of water particles. So then, therefore, from accelerometer records I have directly these quantities, difference in accelerations between flow and water. And in addition, of course, I have these angles, angular velocity, which are proportional just to water accelerations. So then when I calculate when I take this quantity from field measurements, so then I can estimate this coefficient as this ratio. So, and on the next slide, I just want to show you that, so here it is important that I place here omega, so that is like peak frequency of recorded wave. If I have many frequencies, so then I am not allowed to model acceleration with this formula, to express acceleration with this formula. So then I need to differentiate by time or integrate. So then, but then in our situation, so vertical acceleration show very nice peak frequency, about 0.8 radian per second. So therefore, I use these formulas, and here you see that this blue cloud show acceleration of water particles without ice, how it should be, and this is relative acceleration of ice to water particles. So then it is much less. So then ice move almost as a water. So then I estimated this coefficient absolute value like 1/3. So if I go to another type of measurements on big flow, also with small thickness, so that the influence of ice is on this wave is not very important. It is only 30 centimeter thickness. So the same field works few days before. So then we perform on this flow several type of measurements with Doppler velocimeter, with two seabirds, and with set of accelerometers. So then we have also similar spectrum of wave, and we are sure from measurement of different devices that dispersion equation is just similar to gravity waves. So we also did measurements of flexural strength. So we have opinion about elastic modulus that is below 2 gigapascal. So then this ice is nothing for the wave. Elasticity of this ice has very small influence on wave. So then here we have the same picture, and coefficient alpha is evidently is 1. So then it is possible to get this coefficient from field measurements and then take into account in the calculation of dissipation. Another coefficient which I have in model is eddy viscosity nu in under ice boundary layer. So how I calculate this quantity from experiment? So we use acoustic Doppler velocimeter, which is installed on ice, move downward and measure velocity of particle, water particle with volume 2 cubic centimeters. So we program frequency. Maximal frequency is 25 Hz, typical is 10 Hz. So 10 Hz, it means that time of fluctuation is 0.1 second. So that is time scale which we have from our measurements. In addition, of course, we have time scale associated with wave. It is 10 seconds to order difference. And the third time scale is burst time. So then device is working by bursts. So then, let us say, burst length 20 minutes. So it worked 20 minutes, then stop, and then again work next 20 minutes. So then we use this data to split data about velocities into the fluctuations, into velocity of waves, because we have full set of measurements, and we need to tell for the simulations what is velocity associated with wave, where we have fluctuations. We use fluctuations to calculate Reynolds stresses, and what is the mean velocity. Then when we average over the burst time, we have mean velocity. Then we average over the time about 1 second and calculate difference from mean velocity and this average. So then we have wave velocity. So then if we remove from full velocity this quantity, we remove from full velocity wave velocity and mean velocity, then we have fluctuations. And for fluctuations, we interpret them as fluctuation because of turbulence. And we may calculate kinetic energy of fluctuations. We may calculate kinetic energy of waves. We may calculate Reynolds stresses. And then if we divide Reynolds stresses on the mean velocity and distance where we have our device, so then we have eddy viscosity. So these measurements were performed since 2006 in different places of the Barents Sea, and values are quite different. The depth of measurements is about 1 meter, not deeper, usually 1 meter. So biggest value are about 100 square centimeters divided on second were observed here in northeast part to the east from Edge Island, here and here twice in the same place. In 2016, 2012, we got the same. And in other places, values are smaller. And here I only listed those situations when wave propagated below the ice. So then measurements were performed just when we had waves. So actually ADV measurements I perform each expedition, but not in each expedition we measure wave. So characteristics of ice boundary layer. So then relative velocity of water with respect to ice. This is some centimeters per second, sometimes bigger, sometimes smaller. So wave energy, sometimes it is bigger than turbulent energy, sometimes smaller. But in case when we had the high eddy viscosity, then wave velocity was much smaller than energy of turbulent fluctuations. So, and okay, eddy viscosity versus kinetic energy of fluctuations. Of course, if we have high energy of fluctuation, we have high eddy viscosity. We have higher mean velocity of water below the ice. We have higher eddy viscosity. But in case when we had very high eddy viscosity, actually this effect was not significant. Very small dependence of eddy viscosity from wave energy. So this is deployment 4. We had very small wave, so this effect is visible. When we had bigger wave, effect is not visible. Oh. Yeah. What is important? So here you see ice drift velocity. It is not what ice drift velocity reconstructed with GPS data. Then for ice drift, then in situation when we had very significant ice drift, so eddy viscosity was very high. And when ice drift was small, eddy viscosity was small. So this is the last example. So then we have drift velocity 0.1, 0.2 meter per second. We have some wind, tides, so then eddy viscosity is high. So then I expect that this under ice turbulence is coming from the ice drift and not so much from wave. Of course, there is some portion coming from wave, but this portion is visible only if we don't have other sources for the turbulence. So then here, the same place, 6th of May 2016. We have SAR image showing wave penetration from margin from ice edge deeply to the ice, and it is possible to see this wave. So this distance between that and that point is about 5 kilometers. So then what we did, we choose one profile and the second profile and performed pixel analysis to identify main wavelengths. So then again I want to point out that this image was here from 6th of May, and fieldworks were performed this point, just near this point, few days before. So therefore I assume that we have the same turbulent, the same eddy viscosity. So then here you see result of pixel analysis. So near ice edge, we identify this wavelengths about 90 meters, and here it is about 100. So then the difference in peak wavelengths from that analysis is about 13 meters, over 5 kilometers. So then I consider it at the entrance Jones swap spectrum of incoming wave and place the following characteristic for this spectrum. And also I count this eddy viscosity 140 square centimeters per second. Coefficient alpha is equal to 1. I place it 1 because difference between that situation and that situation is that wind change direction and wind compress us ice here, and here we had rare ice. So then I expect that in 5 days we got very compressed ice, and therefore I use coefficient alpha equal to 1. So the length for wave excitation in Jones-Swaff spectrum I took 200 kilometers, water depth 160 meters, and wind velocity was 10 meters per second. So that is from reanalysis. So then this is spectrum on the open water, and then according to this equation formulated before, I have the following change in spectrum. So then on 5 kilometer distance I have peak length on about 0.5 inverse meters, and here we have near ice edge wavelength here. So then peak wave number. So then the difference is also about 13 meters. Actually, I was impressed how these quantities are close to each other, but that is just one example. So conclusions. So flows motion, relatively wave-induced motion of water influences formation of oscillating boundary layer below the ice. Ocean turbulence has influence on this boundary layer and increases wave damping. Inverse influence of wave boundary layer on ocean turbulence, I think, may appear, but it is smaller than this influence, at least for Barents Sea region. Characteristic of flow motion relatively water determine wave energy dissipation. When flow motion is similar to water motion, the damping is very small. Actually, another group deployed accelerometers in the place where we had accelerometer in one point, and their conclusion was that damping of wave with peak length, with wave with peak energy was very, very small, was insignificant. So then that was group of Swain and Closet. So therefore, I am completely agree with that. So then model was introduced with two coefficients, alpha coefficient characterizing motion of flows relatively wave-induced water motion and eddy viscosity. These coefficients were validated for the region of the Barents Sea, and comparison with satellite image gave actually very good results. So I have to give some acknowledgement because several people were involved in this activity, especially International Marine Unit were provided group from University of Oslo, and they also participated in data processing. And a group of UK and Italy experts, Peter Woodhams and Maria Pia, participated in fieldworks and helped to deploy sensors on the ice. So also I had Clarence Collins from Naval Research Laboratory for fieldwork 2016. We performed all mechanical tests together with a group of Russian researchers, and we designed it and built it up together, this equipment. So then I have internship students from University of Lyon, and Vnigas Gazprom provided satellite images with high resolution, and of course students. And project support was provided by Research Council of Norway. It is Project Sankot, Petramax project together with University of Oslo, and Norus project for cooperation with Russian Foundation for Basic Research. So then I finished. So that's end of our activity.
Thank you very much.
Yeah.
You showed the two-star image reduce the wave spectra.
Yeah.
And show the peak wave length increased by 13 meters.
No, difference.
Difference by 13.
Difference between peak wavelengths. So at the edge we have a wavelength about 90 meters. So and 5 kilometers from from ice edge, the wavelength was 13 meters longer.
So what was the conclusion you drew from that observation? I didn't hear.
Yeah, conclusion is that when wave penetrate in the ice, so different parts of spectrum have different attenuation. And that is the reason that peak wavelengths shifted to the range of longer waves. And this effect is well described by dissipation in oscillating boundary layer if we introduce their coefficient of eddy viscosity, which was found for that region.
Okay, so you don't think the wavelength has changed?
No.
I mean, there's no dispersion?
No, dispersion is very... dispersion influence change if we introduce in a dispersion equation some small dissipation, so then, of course, we can calculate the variation of wavelengths for specific value of frequency. But this variation is very small. It will be very small, at least as if a dissipation is realized over the long distance. But just damping for different frequencies is different. So therefore, we have shift of peak wavelengths.
I'm a bit puzzled with the dispersion relation that it shows, because it's for the free surface, right?
Yeah. Yeah.
So, but from the schematic presentation of the problem, I had the impression that you actually have, at the free surface, you have also the ice.
Yeah, I have floating ice, but in all photos I shown that in when we did measurements from the floor, so then ice thickness was 30 centimeters. Elastic modulus measured from test for flexural strength was 0.3 gigapascal, and wavelength was around 100 meters. So then this term was very small. When we work in broken ice, so then we didn't have at all any elasticity. It was just set of flows.
Yeah, but it's not just elasticity, it's also presence of ice, because it's not free surface, it's something floating on it.
Yeah.
So it's also changed the dispersion relation.
It changed, but because of that we have damping. It's changed very small because we performed measurements of we use measurements from 2 accelerometers, several accelerometers on different distances, and we use coherent analysis and found that the dispersion equation just the same as for gravity waves. It is indistinguishable. The same, we did measurements that we have one pressure sensor on one depth, another pressure sensor on another depth, the same point. So we can calculate from those measurements frequency, amplitude, and wavelength, and place that on omega k plate, and we got the same. So we're absolutely sure that local dispersion equation is similar to just gravity waves with free water surface. And damping we have over big distance.
So is it the, does it follow from the length of wave that it's very long, or very long wave? If it should be shorter, then the...
Yeah, for 30 centimeters ice wave should be, maybe if it would be 30 meters, so it would be more. It depends on elastic modulus, on ice thickness, and on wavelength. But in the range of our spectrum, elasticity and other properties, they were small.
Other properties like inertia of the ice, right?
Yeah.
Inertia is it's not important.
Inertia is accounted.
No.
Yeah, it was here in... This is inertia.
But it's inertia of the tangential motion,
Yeah.
not vertical motion.
But we didn't observe big vertical motion relatively water. The flows just move like that. We didn't see this movements.
Okay, so
And these movements don't appear in spectrum. You see, if we would have these movements, we would not have the spectrum. We have 10 Hertz frequency accelerometers placed on the ice. We don't see this maximum.
Mike, please.
Just a really simple question. This eddy viscosity, how does it doesn't appear in the dispersion equation, it appears in this energy loss. But how does it go as a function of frequency? I couldn't see that.
Yeah, but
Frequency.
so this
One small comment.
Stokes problem. You have oscillating plate on the surface of viscous fluid. So then the damping of energy is proportional to square root from product of eddy viscosity and frequency. So if you use wave amplitude for the expression of wave damping to calculate wave energy, so then you have additional coefficient of proportionality between wave amplitude and the water velocity. Then you will have more coefficients which appear and influence damping. So
One comment. I don't imagine that this. I don't know how deep the Barents Sea is, but I've got a feeling it's quite deep. I would have thought you could just assume the depth was infinite. Will you feel like that?
I don't. Your question about how turbulence is distributed.
No. Just the wave. This in your dispersion equation, you have this parameter of the depth, but I'd imagine that you could ignore that and take it as infinite. It would simplify some of the analysis.
No, but dispersion knows about. So here, wave amplitude. I use wave amplitude for the calculation of. So here velocity. So, and here I don't have the depth. I don't have here depth. I have only frequency and velocity outside boundary layer. That's all. But when I consider wave energy, I express wave energy through the wave amplitude. And then there is coefficient of proportionality between wave amplitude and this velocity coming from theory of linear wave. And this coefficient depends on water depth.
Well, let's talk
Could
about
be
it
weakly
later.
dependent.
Again, talking about the eddy parameter, which is a crucial factor in your analysis, you compute it by averaging the Reynolds stresses. You take only two components. I wonder if the other components are not important, or maybe it has to do with your method of measuring the Reynolds stresses using acoustical device instead of using wire, which you can really measure all nine components.
I measure 3 components of velocity.
Yeah, but I mean, how about the other two? I mean, the vertical motion.
I measure vertical and 2 horizontal. We have 3 components of velocity in
So how can you use the acoustical device for measuring all these three directions? Usually you have one direction. Usually we use wire anemometer for this, yeah.
So there is here we have transducer, and that transducer sent acoustic signal. And here we have 3 receivers which got signals under different angles. So 5 megahertz signal, acoustic signal. And these signals, they understand when they should receive this signal, so therefore they are sure that it came from this point. So since we have 3 reflected signals, we have 3 components of velocity. Actually, it measures reflection on particles in the water. If water is very clean, it works not very good.
Okay, so why don't we use it in atmospheric science? Because in atmospheric science we use, wires anemometer.
Yeah, but that is the usual device, acoustic Doppler velocimeter, which is used in the water.
No questions. Everything is clear. So, thank you very much. And special thanks should go not only to our speakers, thanks them, speakers after lunch. We already thank speakers before lunch, but also to the organizing committee of this workshop led by Professor Plotnikov is at the end. So everything what we are doing now, okay, not what we are doing, but how we are doing, it's organized by the organizing committee. So thanks to them and thanks to